All right. Acids and bases. Acids and bases. Let's send this out. We're live. You know it. Boom, boom, boom. Acids and bases tonight. Tune in. All right. Remind sent. Let's get started with acids and bases. Everyone's favorite. So we're at the point where we're reviewing everything from fourth quarter. End of third, beginning of fourth. We did solutions last Thursday. We did kinetics and equilibrium. We're at the hard stuff. The hard stuff of chemistry. The stuff that makes you go, oh my God, why did I take chemistry? It's so hard. We're at those units. So, we are going to just get started. Let's talk about acids first. So, acids. Some general properties, just to review some things from like middle school and stuff. They are a low pH. So, typically we define an acid as under 7. They're sour in their taste. They are considered electrolytes, and we're going to do a lot of stuff with electrolytes later. So we consider them electrolytes. So they conduct in solution. So when you dissolve acids in water and you make an aqueous solution, they will conduct electricity. They will react with a base. And we call that neutralization. So when you react an acid with a base, you neutralize it. It's a double replacement reaction. Meaning, so any acid, typically speaking, we define an acid as any H, which is a positive ion, with some negatively charged species, usually from group 17 or a couple things from the table E. So, if you see H with some negatively charged ion, and you see this AQ next to it, we have an acid. So, generically speaking, when you neutralize an acid with a base, you will always get the same reaction of acid plus base makes any salt, not just NaCl, MgCl2, LiF, any like group 1, group 2 element with group 17, or any group 1, group 2 element with a couple of those guys from table E, like nitrate and sulfate, you get a salt. So NaCl is not the only salt in the world. And water. Anytime an acid-base react, you get a salt and water. So, for example, if you take any generic acid, HX, plus any generic base, I'll do Y with OH. So here the Y is positive, the OH is negative. In here the H is positive and the X is negative. You get a double replacement reaction, where the two positive ones just swap with each other, or the two negative ones swap with each other. It's the same thing. So you get HOH. So these are switching. And HOH is just H2O, which is water. And then YX. Whatever Y is and whatever X is, they will combine. You will find a whole list of acids on table K. So a lot of times, if a question just says, is this an acid? There is a good chance it is on the reference table on table K, which says common acids. So if you need to identify an acid, there's a good chance it's on here. I've seen some years, I've seen ones pop up that are not on here, like HBr. But the the general formula is the same. There's an H, there's the H in this one, with some negatively charged ion, whether it be from table E or from the periodic table. There is something with a negatively charged ion. That's the general formula for an acid. Arrhenius. The Arrhenius definition of an acid. He defined as acids as they produce H+. In solution. So he gave it that general formula as an acid is HX, where X is any negative ion, and that's how he defined them. So he said when you dissolve these in water, so if we take our acid, let's say HNO3, nitric acid, and you dissolve it in water, they will form H's and the other ion, which is negative, NO3. And these are all aqueous. Aqueous and aqueous. Alright, so that is the Arrhenius definition of the acid. Then there's the Bronsted-Lowry definition of an acid, but the Regents, for whatever reason, doesn't use those terms. So you're going to see it worded as the alternate theory for acids and bases. And the alternate theory for an acid is that in a reaction, they donate H+, or they donate, sometimes they'll word it as a proton. So, an acid in a reaction would, let's say, for example, you see a reaction like this. You see this happening. You just have to look on both sides, read it from left to right, and see which of these two donated an H. And since H2O became OH minus and NH3 became NH4, I can go ahead and say that H2O took one of its H's, gave it to NH3, so NH3 gained an H, and H2O lost an H. So this is an acid, and this is a base. And then from right to left, reading it backwards, NH4 donates one of his H's back to OH, making OH a base, and NH4 an acid. So that is the alternate theory of acids and bases. And now I'm going to talk about bases. So that's basically a good summary of acids there. pH under 7, generically speaking, they look like H+ with ion X. Whatever X is, could be from group 17, could be from table E. As long as it's aqueous, it's an acid. They're sour in taste. They're considered electrolytes, so they conduct in solution. When you react them with the base, they will neutralize. That's a double replacement reaction, where any acid plus any base will make a salt, any salt, and water. And you'll typically see these with strong acids and bases, because we don't deal with like weak ones too much in neutralization on the Regents. So again, generally speaking, if you have some acid, HX, and some base where bases have OH, when they react, the two positive ions, H and Y, will switch, and the H will go with the OHs to make water, and the Y will go with the X to make whatever that is. And we'll do an example later where we have to check our charges. Table K is where you'll find all the acids. All the acids on Table K are pretty much Arrhenius acids, and he defined acids as producing H+ ions in solution. That's what it looks like with nitric acid when they dissolve in water. The alternate theory of an acid is in a reaction, it donates an H, or donates a proton. So if you look at this reaction, H2O lost an H, gave it to NH3, and turned into OH. And NH3 turned into NH4. So H2O is the acid, and NH3 is the base. And then going backwards from right to left, NH4 will get rid of its H and give it to OH minus, and turn that, and in turn, NH4 there is the acid because it donates an H, and OH minus is a base because it accepts an H. General properties of bases. pH is greater than 7. All right, their pH is greater than 7. They tend to taste on the bitter side. They are considered electrolytes. So they also conduct electricity. Much like an acid could react with a base, they react with acids. And they neutralize each other, especially when they're both strong. And let's do an example of that one with real ones. Let's pick something from table K. Let's do MgOH2. That's our base. Sorry, from table L. So bases, there's very few of them they'll give you. But, again, doesn't hurt to check. If you're dealing with a base, you might as well check table L. These are all common bases on table L. Most of them have hydroxide in it. The only one that kind of sticks out being different is ammonia. Ammonia. Alright? So, I am doing MgOH2. Actually, I'm going to do CaOH2, because that's from table L. CaOH2 with, change color here, let's do HCl. Now, when you neutralize these, I ran out of room, so I'm just going to write it below. Again, the positive ions will switch with each other. So when you look at a formula that's ionic, the positive ion's always going to be the first one. So I'm going to take that Ca, I'm going to take that H, and I'm going to switch them. And don't be a subscript dragger. Don't drag that across left to right. Leave that where it is. You get HOH and CaCl. Now you might think you're done. You're not. Anytime you have a double replacement reaction, make sure you go to the periodic table and check your darn charges. Ca has a charge of +2. So when it bonds to Cl, Cl will have a charge of -1, because opposites attract. And since it's ionic, since it's a metal and a non-metal, one of them has to be positive, and one of them has to be negative. And the metal is always positive, because the metal doesn't like electrons as much as its non-metal friend. So, since this is +2 and this is -1, not -7, -1, that doesn't balance. So crisscross these, just the numbers, down. So your final answer should be CACl2. CACl2. Alright, so that's just my dog moving around. So, yeah. So you can find bases on table L. And Arrhenius had a definition for bases like he did for acids. So Arrhenius said bases produce OH minus in solution. So generally speaking, he said that bases have this generic formula, where X is almost always a group 1 or group 2 element. Because those are how we typically define our strong bases. The alternate theory for a base is in a reaction, it will accept an H plus or proton. It means the same thing. It just depends on how the problem words it. All right, so it'll accept an H or a proton. So, for example, if we think of another one, we have HF plus H2O makes F minus plus H3O. Here, the HF lost this H and gave it to H2O. So HF is donating an H, and H2O is accepting an H. And then if you read it right to left, to go backwards, one of the H's from H3O has to go back and attach to F. So F becomes the base on the right-hand side, while H3O is the acid. Let's see. All right, key thing about electrolytes. Electrolyte. They like to ask question about electrolytes. They like to ask the question of why does blank conduct? You have to explain. And if it conducts in solution, like not why does potassium conduct? Potassium conducts electricity because it's a solid chunk of metal. And it has a lot of moving, mobile valence electrons. Electrolytes conduct because they have moving, charged particles. So we have to keep this phrase in mind. Moving, charged particles. Electrolytes have moving, charged particles. So, what are some things we consider to be an electrolyte? Acids and bases are electrolytes, and any ionic compound, so any compound with a metal and a nonmetal, because that's what an ionic compound typically is, a metal and a nonmetal. So, when you have a question about an electrolyte, and there's a lot of times where these are multiple choice, they give you options, like which one of these is an electrolyte. Check table K, check table L, or see if there's a metal with a nonmetal. See if you see a compound with a metal in it. Okay? Because they love that question. Sorry, I'm getting a text from one of my students here. Of course, there's an attachment, which can only mean it's a meme. Yep, that's terrible. Okay, I'm going to ignore that. So, those are electrolytes. All right, we did acid-base theories. Okay. We did Arrhenius. We did the alternate theory. We did electrolytes. Let's talk about pH. So, when I start talking about pH, there's something to keep in mind. pH is a measurement of H plus ions. However, these H plus ions will tend to form a different compound with water. So it's also a measurement of H3O plus ions, where H3O plus is on table E, and that's hydronium. So, in any given acid-base solution, there's some H plus and some OH minus. So when you multiply them together, every acid-base solution has some concentrations of these. You should get 1.0 times 10 to the negative 14. Where again, let me write that like this. You can multiply H plus or H3O plus because they go hand in hand. H plus and H3O plus go hand in hand. So I'm going to keep them together for the rest of this video as much as I can remember. But every acid-base solution has some amounts of OH minus and H pluses / H3O plus. So when you multiply them together, you'll always end up with 1 times 10 to the negative 14. So as you increase H plus and H3O plus, that means you're increasing the acidity, which results in a lower pH, because acids have a low pH. So as the concentrations of your H plus goes up, the value of your pH is going to go down, because as you increase H's and H3O's, H's / H3O's, you're increasing how acidic your solution is, which means the pH of your solution is going to get smaller. Conversely, if you decrease your H plus / H3O plus, you're becoming less acidic, which means your solution is gaining more, I don't want to say basicity. The word for this is alkalinity. It's becoming more alkaline. Alkaline. I forgot it now. Alkalinity. So, alkaline means base. Alkaline means base. So if the H plus / H3O plus is going down, you're increasing how basic your solution is. You're increasing how alkaline your solution is, which means your pH is going to start going, I hate it when I do that. Your pH is going to start going up. All right? So you can kind of visualize it in this weird looking table. So the pH scale goes from 0 to 14, where 7 is neutral. As you are at 0, let me redraw this table. Goodness, Mr. G, you're awful. 0, 7, 14. Over here, there's a lot more concentrations of H plus / H3O plus. And as you head towards 14, that concentration gets smaller and smaller. While at 0, you don't have hardly any OH minuses, and as you creep towards 14, your concentration of OH minus is getting larger and larger and larger, because H's measure acid, H plus is a measure of how acidic you are, and OH minus is a measure of how basic you are. OH minus is a measure of how alkaline you are. Now, on the Regents, you're going to start seeing H's and H3O plus ions given in some concentration of 1 times 10 to the negative x. pH is just equal to x, not negative. So, if there's a problem that says your H3O plus concentration is 1.0 times 10 to the negative 9, your pH is 9. You're always going to see numbers that are 1 times 10 to the negative something. If you see an OH minus concentration of 1 times 10 to the negative 9, that means your H / H3O plus is 1 times 10 to the negative 5. Because remember, the OH and the H pluses, these have to add up to 14. Okay? So your OH minus and your H plus concentrations have to add up to 14. So your pH, once you've converted it to the right number, here is 5. So the less OH you have, the less H3O plus / H plus you have, the more basic you are. The more you have, the more acidic you are. One of the biggest missed questions on the Regents. For every times 10 increase in H3O plus, that is a 1 unit decrease in pH. So, let's say the pH was 2.5. H3O, and they'll usually word it like this. H3O, let me write below it. H3O increases 100-fold. So it says H3O increases 100-fold. That means it increases 100 times, which is equal to 10 times 10. So every time you multiply H3O plus times 10, the pH goes down a unit of 1. So there's 2 increases, 2 multiples, -1, -1, and your final pH is 0.5. So do 2.5 minus 1, take that answer, subtract 1 again, and you end up with 0.5. Every times 10 decrease in H3O plus / H plus equals a 1 unit increase in pH. So, let's say the pH changes from 3 to 6. That's 3 steps up. Your H3O plus decreases 3 multiples of 10. So it decreases by 1,000 times. So, for every times 10 decrease in H3O plus / H plus, that is a 1 unit increase in pH. So if the pH goes up from 3 to 6, that's 3 steps, 4, 5, 6. Your H3O plus concentration is going down by a multiple of 10, or a power of 10, 3 times. So 10 times 10 times 10 is 1,000. Now, how can we relate this to OH? And then we'll do indicators, because we already did neutralization reactions. And then we'll do titrations. And yeah, so generally speaking, as H plus / H3O plus is going up, your OH minus is going down, and vice versa. Is going down, your OH minus is going up. So, the same rules kind of apply here. If your pH is going up 3 steps, from 3 to 6, your H3O plus is going down times 1,000, which means your OH minus is going up times 1,000. And in the first example, if your H3O plus increased 100-fold, your pH goes down to 0.5. That means your OH minus decreased 100-fold. they're polar opposites of each other. If H plus measures acids, OH minus measures bases, they're going to go up and down. They're going to vary. If they're equal to each other, so if you find that the H plus or H3O plus concentration is equal to the OH minus, well, that means it's neutral. Your pH is 7. Okay, I'm just going to go over really quick how to read table M, which is your indicator table. It's an easy table, but how do you read it? So, methyl orange, all of these going down. I'm going to highlight them the appropriate color. I'm going to do yellow first, because most of these are yellow. Alright, then I'm going to do red. Pink. And blue. So, how do I read table M? Everything on this side, so the left-hand side, at a pH of 3.1 or lower, methyl orange will be in color of red. At a pH of 6.0 or lower, bromethymol blue will be yellow. At a pH of 8 or lower, let me get rid of that color. Phenolphthalein will be colorless. Litmus, 4.5 or lower, red. Bromcresol green, thymol blue, 3.8 or lower for bromcresol, yellow. 8.0 or lower for thymol blue, yellow. Same thing on the other side. Methyl orange, 4.4 or higher, yellow. Bromethymol blue, 7.6 or higher. Litmus, 8.3 or higher. Bromcresol, 5.4 or higher. Thymol, 9.6 or higher. Those are all blue. Phenolphthalein, the one we use in the titration lab, at 9 or higher is pink. So I'm going to put a bunch of problems, just like I've been doing, on acids and bases, and there will be a bunch of problems on these indicators to give you practice using this table correctly. But that's how you read this table.
Hi, Mr. G.
Hi. How goes it?
What?
You come bearing gifts.
Ice Pops.
I love ice pops.
Buffalo chicken dip. Are you live streaming?
Yeah.
What up, chemistry?
I don't know how many are watching.
That's okay, I'll watch it later.
Sure.
Totally.
Where'd you get the ice pops?
Hannaford, do you want one?
Yeah.
After your live stream?
No, yeah.
Okay.
Yeah. Because I have a...
Harper, go live stream. Go live stream.
Harp, come here.
Has she made an appearance yet?
No, this is her first one. Hi. Come here. There you go. Yes. Look at the camera. See ya.
No, Mom has food.
Mom has food. All right.
Come on.
Hey, Sophie said I love her.
Hi, Soph.
And I'm assuming she's talking about you. She could be talking about Harper.
I know, it's hard to distinguish us. We look really similar.
Well, you're both female.
That is true.
So there's that.
You're nailing it right now. All right, keep talking about chemistry.
I'm going to try.
Come on.
All right, where do I want to go next? Where do I want to go next? Do. She said she loves both of you. Thank you, Soph. Soph a loaf. All right. Titration. Last topic. Last thing we're going to talk about. So, titration. You use titration to calculate an unknown concentration aka an unknown molarity from a known molarity. And often a known molarity, a known concentration. And more often than not, when you see the word titration in a problem, or you see the word neutralizes in a problem, you're going to use the equation MA VA equals MB VB, which is given to you on the periodic table. Not the periodic table, the reference table. So, boom, titration / sometimes you'll see the word neutralization in the problem. MABA equals MBVB. MAVA equals MBVB, where it tells you what all the variables mean, as it always does. A is all about the molarity of your acid and the volume of your acid. B is always about the molarity of your base and the volume of your base. So, for example, and then I think we'll call it a night. Call it a night. What is the concentration of HI if 0.3 liters is keyword neutralized? By 0.6 liters of 0.2 molar KOH. So first, identify your acid and base. H in front, acid. OH in the back, base. Volume of your acid right here. So that is your VA. Volume of your base. Concentration of your base. What is it asking for? The question is, what is the concentration of HI? Where HI is your acid. So, concentration of our acid is unknown times concentration of volume of your acid equals concentration of your base times volume of your base. So, unknown times 0.3 equals 0.2 times 0.6. Divide both sides by 0.3. Divide both sides by 0.3. And I believe you get an MA of 0.4. I think that's about it. Sometimes we'll throw in questions on table J, which we've seen before. We love table J. All have H's in it. So, we know acids have H. So anything that's above H, any metal above H, will react with that acid. So, for example, let's take Mg. No, let's do Zn. If you react Zn with HCl, it is, let's say, more chemically active than the H. A single replacement reaction occurs where H, why is it H2? Brinkelhoff, when you chemically react things, always remember that these are all diatomic. They are always two when they are alone in a chemical reaction. Then for zinc, check your charges. On the periodic table, zinc is charged +2. So we got to crisscross that 2 going down. balance your equation. More often than not, you won't be asked to do everything I just did in one question. It'll either be a series of steps, there will be fill in the blanks, or it'll already be to pick the right product. But generally speaking, how to use table J is always the same. If the metal is above H, it will react. It will react spontaneously. This will occur without you doing anything. All you have to do is take some zinc and just plop it in some HCl, and it's going to start bubbling. Have a great night. I will get this video and last night's video on my teacher site tomorrow with practice problems and an answer key as usual. You guys are the best.